Hello. In this lecture, we're going to be taking a look at one of the most important equilibria that exist in nature, something called the self-ionization of water. To introduce this topic, we need a few definitions. Substances are often divided into three categories, what are called non-electrolytes, strong electrolytes, and weak electrolytes. And this definition, this breakdown, is based upon whether or not when you dissolve these substances in water, the solution that's formed will or will not conduct electricity, and how well it will conduct electricity. A non-electrolyte is defined as a substance which, when you dissolve it in water, produces a solution that does not conduct electricity. A strong electrolyte is a substance which, when you dissolve it in water, and we will assume it's soluble, is an excellent conductor of electricity. And a weak electrolyte is a substance which, when dissolved in water, the solution conducts, but doesn't conduct electricity that well. It just conducts electricity a little bit. Here's some examples of these three types of substances. Sucrose, sugar, common ordinary table sugar, C12H22O11, that's classified as a non-electrolyte. And the reason it's classified as a non-electrolyte has to do with the following idea. Something will conduct electricity if it forms ions in solution. In an aqueous solution, you can't have electrons moving up and back, so if there's going to be any conduction, it's going to have to be due to the movement of these charged ions. Well, if you look at what happens when sucrose dissolves in water, basically nothing happens, it just dissolves. You have molecules of sucrose in solid table sugar, and when it dissolves in water, and here's the key, it remains molecules. The molecules don't break apart into ions, they don't break apart into carbon, hydrogen, oxygen, or anything. They just stay together as sugar molecules. And they float around, they swim around, that's it. Since there's no charged particles there, no ions, sucrose is a non-electrolyte. An aqueous solution of sucrose will not conduct electricity. This can be contrasted quite nicely with an aqueous solution of sodium chloride. That's common ordinary table salt. When you dissolve sodium chloride in water, wow, you get nothing but ions. It breaks apart 100% to form ions. So dissolving salt in water produces a solution that contains just a plethora of sodium and chloride ions. Now, it doesn't matter what kind of ions there are, but there are ions. So this should be an excellent conductor of electricity. And we can contrast this to another common substance you find in your home, acetic acid. Now you might say, no acetic acid in my house. Yes, there is. Probably vinegar is an aqueous solution of acetic acid. What is water? Pure water. Is that a strong electrolyte, a non-electrolyte, or a weak electrolyte? Most students, good thinking students, will say, well, I don't know about the strong and weak part, but I know water conducts electricity, so it must be an electrolyte. And they base this upon the fact that they've probably heard never to, for example, let an electrical appliance fall into a bathtub because you get electrocuted. That water, quote, conducts electricity. But that's misleading. Tap water will conduct electricity. Pure water basically doesn't. And the reason tap water conducts electricity isn't because of the water, it's because tap water has dissolved minerals in it. Minerals are ionic substances. So virtually any conductivity you see in tap water isn't due to the water itself, but is due to the substances that are dissolved in the water. If you obtain highly purified water, distilled water, it is essentially a non-conductor of electricity. It's virtually a non-electrolyte. I brought some of these substances into the studio today, and I think it might be fun to test this conductivity idea on some of the real substances that we have discussed. On the table in front of you, you see, well, I guess I could say 5 beakers, but it's 1 beaker and 4 glasses. I think we can safely assume that if I use a beaker or a glass, that doesn't make any difference. Inside the first container, I have placed distilled water. You'll have to trust me on that. There's no way I can prove that. But have I ever lied to you? In the first container, I have indeed placed distilled water. I have here what is called a conductivity apparatus. It's a pretty simple apparatus with a small light bulb. If I place this into a solution and the light bulb lights up, that means the solution is conducting electricity. There are ions in that solution. The substance is an electrolyte. If the light bulb doesn't light up, that indicates that at least within the sensitivity of this test, I cannot detect any ions, and therefore I would consider it to be, quote, a non-electrolyte. Let's see what happens with distilled water. Well, that's real exciting, isn't it? Within the limitations of this particular test, distilled water, which you will consider to be pure water, does not conduct electricity. It doesn't appear that there are any ions there. The glass next to this contains tap water. Again, you'll have to trust me on that. I literally went to the tap about 10 minutes ago and just filled this glass with water right out of the tap. Let's see if there's any conductivity in Virginia tap water. There's not a tremendous amount of conductivity, but we certainly can see that tap water is a conductor of electricity, and it happens to be due to the substances that are dissolved in the water, not to the water itself. In the third beaker, I have again placed distilled water. We know that distilled water doesn't conduct. In fact, we can sort of verify that. Certainly there's no conductivity there. And now I'm going to dissolve into that water some common, ordinary table sugar. Once again, you'll have to trust me on this. This is common, ordinary sucrose, table sugar. No conductivity in the distilled water. Sucrose. And it doesn't appear that I can get any conductivity from the sucrose either. Just as we said, sucrose dissolves in water to form only molecules. Molecules won't conduct electricity. There are no ions. So this, again, is a non-conductor, a non-electrolyte. What about salt? Well, I just happen to have some salt over here. So let's take a scoop of salt, sodium chloride, common ordinary table salt, and see whether we can detect any conductivity in a salt solution. Once again, the distilled water does not conduct. Can we detect any small conductivity if I put salt in there? Wow, that didn't take long. I didn't even have to wait for that stuff to dissolve very much. Salt is obviously an excellent conductor of electricity. It is a strong electrolyte. It ionizes 100% to form ions. I'm going to rinse this in the original distilled water to get any of the salt off of the apparatus. And then in the last beaker, I'm going to pour 1 molar acetic acid. Again, you'll have to trust me, but if you detect the odor, can you detect the odor of that? It smells just like vinegar, doesn't it? 1 molar acetic acid. There's nothing in the beaker now except air. Well, acetic acid certainly conducts electricity. This is clearly some sort of an electrolyte. But is it strong or weak? I claimed it was weak. Well, if we contrast its conductivity to the salt, you may be able to detect the difference, but then again, you may not. I suppose you can see that this light bulb is somewhat brighter than when it was in the acetic acid. But the problem I have here is I'm using too small of a light bulb. The test is, in essence, too sensitive. So to try to distinguish whether there really is any difference in conductivity between the salt solution and the acetic acid solution, I'm going to replace that small light bulb, which was something like 7.5 watts, with a 40-watt regular incandescent light bulb. Let's see if we can detect any difference. Acetic acid. Can you see the faint glow? Let's see if there's any difference with the sodium chloride. Well, that test certainly shows us that there is a significant difference in the conductivity of the salt solution versus the conductivity of the acetic acid solution. In fact, the little extra glow you see is probably due to a little bit of the salt that was left on these electrodes. Sodium chloride is a strong electrolyte. It ionizes 100% in aqueous solution. Acetic acid, on the other hand, is a weak electrolyte. It only ionizes, let's say, 0.5% in aqueous solution.